Hello students, the question here today says a particle of mass m is kept on the top of a smooth sphere of radius r. It is given a sharp impulse which imparts it a horizontal speed v. Find the normal force between the sphere and the particle just after the impulse, that's part A. Part B is what should be the minimum value of v for which the particle does not slip on the sphere. And part C is assuming the velocity v to be half the minimum calculated in part B, find the angle made by the radius through the particle with the vertical when it leaves the sphere. So let's work upon this question one by one, starting with the first part. Finding the normal force between the sphere and the particle just after the impulse. See that because of the impulse, because of this sudden striking the particle acquires a velocity v in the horizontal direction. Do we understand that because of this velocity, the value of forces that it exerts on the surface now will change, because if we try to write the equation of forces along the radial direction, which will also be the vertical direction here, do we see that the only forces acting on the particle are normal reaction acting in the upward direction from the surface and the weight of the particle mg acting in the vertically downward direction? And if we try to write the force equation along the radial direction, F net is equal to mass into acceleration, which in this case we are writing along the centripetal direction, so it's the centripetal acceleration. Can we write this as net inward force, net radially inward force, which is mg minus n is equal to mass into centripetal acceleration we know is given by v squared by r. So from here we can easily calculate the value of n, the normal reaction that the particle will experience from the surface and which also the particle will exert on the surface, right? So this is the value for n that we will get at the topmost point. The second part of the question says what should be the minimum value of v for which the particle does not slip on the sphere. Do we understand what is the meaning of the particle not slipping on the sphere? What is the other way around? What else can happen if the particle does not slip over the sphere? What will happen is the particle will simply fly off. It will lose contact from the sphere and will move straight as a free particle without experiencing any normal reaction, any normal force from the sphere, because it is no more in contact with the sphere. Had it been slipping on the sphere, it would have had some contact force coming from the sphere. So we directly say that the condition for the particle not slipping on the sphere would be that the normal force between the particle and the sphere goes to 0. And we already have the expression for normal force with us, right? So all we need to do it is put n is equal to 0 in the above equation, which gives us mg minus m into v squared by r going to 0. And from here we can easily find out the value of v. V will come out to be root of gr, isn't it? Do you see that? After solving this equation we can get this easily. Now going to the third part of the question, which says that assuming the velocity v to be half the minimum calculated in part B, this is the value of v that we have calculated in the part B. So according to the situation now, we have the velocity in the third part v to be equal to root of gr by 2, right? Half of the velocity in the part B. And now we are supposed to find out the angle that the particle will make with the vertical when it leaves the sphere. So if we assume that, let's say, the particle leaves the sphere at this point, do we understand that once again we can say that since the particle has traveled some height down, it would have acquired some velocity at the expense of losing its potential energy. With that velocity, then we can write the force equation saying that the normal reaction in the radially outward direction and the component of mg in the radially inward direction, which will by the way be mg cos theta. If we assume this angle to be theta, we can write the force equation here as mg cos theta minus n is equal to mv squared by r and put n is equal to 0 there, right? So these are the two steps that we shall be doing. First step is conserving energy, conservation of energy between the points A, the starting point, and the point B where the body is losing contact, between A and B. So at the point A, we say that if the potential energy is mgh, assuming that the potential energy at B is 0, so that the loss of potential energy as the particle moves from A to B will be equal to the gain in the kinetic energy as it moves from A to B. Gain in kinetic energy means the final kinetic energy, which will be some half m v dash squared, if we assume that the velocity at the point B is v dash, minus half m v squared, which is the starting velocity at the point A, which we have already, which has been given to us. So we need to substitute its value over here, right? Now here, what is the value of h? Let's look at the figure once again. See that the h value can be calculated using this length, which is nothing but r, and this length, which is nothing but r cos theta. So our h value comes out to be r minus r cos theta, and we can substitute it here, so that we get, okay, maybe we will do it a little later in the second equation. Now we can write the force equation for the particle at the point B along the radial direction, of course. So as we have just now discussed, along the radially inward direction, the net force will come out to be mg cos theta minus n, but now n goes to 0, as we are saying that at the point B the particle loses contact with the sphere, and this net radially inward force must be equal to the mass into the centripetal acceleration, which will be v dash squared by r. Yes, and now we can solve these two equations, the conservation of energy and this force equation, together to get our value for whatever is being asked for, the angle theta, that is. So maybe here m goes away, and if we take r on the other side, in this equation we will get gr cos theta is equal to v dash squared, and the value of v dash squared from here can now be substituted back into this equation over here. Yes. So let us solve this equation now, the conservation of energy equation, which will give us mg into h value will be r into 1 minus cos theta is equal to half m into v dash squared, which from this equation is gr cos theta, minus half m into v squared, this v squared which we know here is root gr by 2. So when we square it will be gr by 2. Yes. When we solve this equation completely for the value of cos theta, we can easily prove that the value of cos theta here comes out to be 3 by 4, and the value of theta corresponding to that will be cos inverse of 3 by 4, which will be the final answer for the question.